Hello, my name is Yining Chen. I'm from Stanford, and I'm presenting our work on active online domain adaptation. This is a joint work with Haipeng Luo, Tengyu Ma, and Chicheng Zhang. Domain shift is a major challenge for many ML systems. Consider the self-driving car system. It needs to adapt to changing data distributions on rainy days and sunny days across time. Online learning is a classical framework that studies worst-case domain shift. At every time step, an input xt is chosen by an adversary. The learner predicts y hat t, suffers some loss, and then the label yt is reviewed. However, acquiring the label at every time step is very expensive. So in this work, we study active online learning, where the learner can decide whether to query the label. We study active online regression, where we start with the hypothesis class f. We consider the realizable setting, where the label is generated by f star in f plus a white noise. At every time step, the loss is measured by the squared difference between the label and the prediction. We have two metrics. One is the total number of queries q, and the other is the cumulative regret across time steps. Our goal is to minimize regret subject to budget constraint less than or equal to b. As warm-up, let's consider linear regression. So here the hypothesis class is theta transpose x, where theta is a d-dimensional vector. Let qt denote all queried examples up until time t-1. Given the queries, our prediction strategy is to simply follow the regularized leader. Now the question is how to make the queries. As a baseline, let's consider full queries. If we make query at every time step, q is equal to t, and r is on the order of d. If we uniformly randomly query with probability mu, which is said to be over t, then the expected number of query is b, and the expected regret is dt over b. We can do better when the data is more structured. Specifically, we consider the following domain structure. There are a total of m domains. On a domain U, we denote the dimension of the support by du and the duration of the domain by tu. If we can make fewer queries on easier domains, we can save budget for harder domains. Our main contribution is that we provide an optimal trade-off when the learner does not know the domain structure a priori. Our algorithm QFER queries uncertain examples more often. For any domain partition with high probability, we bound the regret by parameters du, tu, and budget b. We provide a matching lower bound to demonstrate that our bound is tight, and we also generalize to general hypothesis classes. The key of our algorithm is building an uncertainty estimate for unlabeled data xt. We measure it by delta t, which is related to the empirical covariance matrix. We query the label proportional to delta t. For general hypothesis classes, we generalize du, which was the dimension of the support, to d prime u, which is the eluder dimension. The eluder dimension measures how effective the potential value of acquiring a new label can be estimated from labeled examples in a domain. We first build a confidence set which consists of all hypotheses that have bounded empirical laws. Then the uncertainty measure delta t for xt is just the square of the max disagreement between any two hypotheses in the confidence set. We also provide a similar regret guarantee that's in terms of the eluder dimension, the log covering number, tu for each domain, and the budget b. We perform experiments on two regression tasks and two classification tasks. Across all four datasets, our algorithm QFER in green line has the best trade-off compared to two baselines. One is the uniform queries baseline, and the other one is a greedy baseline where we make queries at every time step until the budget runs out. In conclusion, we proposed a novel task of active online learning when there is latent domain structure. We propose a simple algorithm that can adapt to domain shifts, and we provide matching upper and lower bounds for linear regression. And finally, we generalize to general hypothesis classes. Thanks.